Harsh, again, thanks for your time and coming up to this meeting. Today's session, we are going to talk about. I guess it's fair to say, talk about rollups because you are a rollup expert and you have been working in the zk rollup for quite some time now. But now you wear a bit of a different hat, but I guess in the similar domain. So let's just kick off. I will try to be mute and give it to you, Harsh.
Got it. Cool. So thanks everyone for coming. So thanks for the introduction, Saf. First of all, a little bit introduction of me. My name is Savish. I've been working in the crypto industry for I guess more than 3 years now. And I started my first big work was with Polygon. So I spent some time at the ZK team at Polygon, and then I spent an year building a zkRollup tool. So then I've spent like a year working on a new zkVM project, which was Kakarot, and it was a layer to zkRollup. And now I'm working at Fuel, which is again a hybrid rollup. It's both we have zk proofs, but at the same time, by default, it's optimistic in nature. So I guess I've spent like considerable time in the industry doing rollups. And I guess the mode of presentation would here be like me just trying to sketch and whiteboard stuff and trying to explain how rollups work and how we have been using zero knowledge proofs in rollups. And then at the same time, I will try to give some deeper insights into like how the rollups have evolved, like how zk rollups have evolved and how the zk technology has evolved, and like how I would make a rollup today versus how I would have made a zk rollup back when Polygon and everyone else started it. And I guess that would be the really interesting part and a really interesting insight. At the end, I might try to take some time to talk about privacy, which would be that I might try to explain a little bit of Tornado if time is left. But I think with Tornado Cache, I haven't followed privacy-based implementation for quite some time. So like a lot of Tornado Cache stuff has really advanced. So we will keep it at the end if time is left, but we will start with zk-based rollup. So first of all, how many of you do have some sort of an idea of what a rollup is? Just feel free to reaction, emoji. That will just help me get some idea of context. Okay, I guess Hitler has context in it, and okay, Saf has. Okay, cool. So for everyone else, let me just try to simplify. What are rollups and so let's just start with what even are rollups, right? So we have this, we have a blockchain, right? And then let's say this blockchain is a blockchain like Ethereum. And the thing is that the blockchain has this fixed atomic unit in which it bundles transactions and executes them. So for example, in case of Ethereum, in case of Ethereum, every block can bundle up to transactions till 30 million gas has been consumed. If I'm correct, that's the amount of gas that you can do in a block. So what it means is that Ethereum is a trust computer, it's a trust machine, and it's a place where everyone is trying to settle the truth. Everyone believes it's decentralized, everyone believes it cannot be tampered with, and everyone believes that there is a lot of economic guarantee to protect Ethereum. But the issue is that for a chain like Ethereum, the processing unit, a block, is finite, which means that at any given instance, right, it can only do certain amount of transaction. And that's the nature of any blockchain. You can just not surpass that limit. All blockchains will be constrained by some limits, and you just cannot do more transactions than that, right? So that is how blockchains work. There's blocks and blocks bundles transactions. Now the issue is that with Ethereum around 2018, 19, I guess something like that, so initially everyone thought that the whole internet will be built on top of Ethereum. People were building job posting job advertisement boards on Ethereum and everything. Like people were just like someone made, I remember, a Twitter on Ethereum where every tweet was actually being inscribed. Inscribed is not the right word, but like being written permanently to Ethereum. And we never got into any scaling issues because Ethereum never had like such a high demand for it. But after CryptoKitties, something really changed. Like there was this game called CryptoKitties, like where you can you had like these virtual kittens and you could like they could evolve and there were a lot of dynamics involved in it. And that's where Ethereum really saw the first scaling issue. Like it was the first time where people wanted to use Ethereum, but they no more could because it was so much expensive, right? And and the reason is simple, right? Let's say if there are like X number of transactions which a block can do, but the demand is, let's say, more than X, right? Then you can only bundle up to X in a block, and all of these transactions have to wait for the next block to be produced, right? And if this size is very high, like your transaction waiting time will keep going up and up and up. And that's a very bad issue from a UX perspective. And then the second issue is that it's a matter of financial inclusion. Right? So if you look at, so Yuga Labs, I guess, did this, Yuga Labs did this virtual, they were selling virtual land on top of Ethereum, if I remember correctly. And then the issue was that the demand was so high that like Ethereum became like unaffordable for most people to go and make. Like the gas was so high, and that makes you realize that like at scale, blockchains suffered from the problem of financial inclusion. Like, how do you guarantee someone financial inclusion? Imagine if this was like some auction happening for some real land, and the gas is so high that a normal people, like person like me, you, or anyone else, can no longer bid because gas is too high. It's just unaffordable, right? Like someone is willing to like outbid you in terms of gas, and that's purely because of this finite resource of how much compute you can do in a block. So uh, that's like this scaling issue, right? So blockchains have this inherent scaling issues, and someone might ask that, oh, but why can't we just go the Solana way? Why can't we just use a really big box and like allow for way more transactions to happen? So there are like two cons in it, right? There are like two things to notice. One is that you really have to make a differentiation between, so you really have to decide your hardware requirements, right? And in case of Ethereum, till this far, it has been that uh, a validator should be something that anyone should be able to run at their home, at their place. On the other hand, in case of Solana, they are pretty fine with validators being outside of the scope of someone being is easily able to run them at their home. Second thing is that regardless of how much throughput a chain can handle, there will always be more demand. So it doesn't matter if you can do 50,000 transactions per second, 60,000, 100,000. You will eventually run into the same issues where like you have a finite resource and the whole world wants to use it. So that's the scaling problem. And then there were various solutions around it. So I could say Polygon POS launched this other thing called the like Polygon launched this chain called POS, which was a side chain to Ethereum. But the issue with the side chain is that they like their security is the security of their validator network, right? So although they can connect with Ethereum and they can talk with Ethereum, but it doesn't mean that it's as secure as Ethereum. But on the other hand, what's the value prop of blockchains? It's that it's a real decentralized network and it's immutable and it is censorship resistance free. You want your contracts and your money to be in a place where something like OFAC cannot affect it. To be cancelled and no one can just wake up and cancel you up, right? So that was one of the issues. So the industry tried with for some time with side chains and with like there were other side chains as well. Like DAI came up, like Gnosis had a side chain, it still has one, I guess. So like a lot of people tried building various side chains and thought that could be a way to scale Ethereum, but every time someone would go to a side chain, like they would lose on security on a side chain model. So then this new primitive called a plasma came up, and we'll not get into plasma because right now they aren't actually being used in Ethereum at any particular place. But they had their own set of difficulties. Like it was very hard to scale plasma networks, and it was very hard to make very sophisticated networks out of them. At least from what I know, and I haven't been very deep into plasma, but it was very hard to build one. Like the OP guys were working on plasma before working on optimism, and that's where that's where I would say John Edler was the first person who published some real paper around it. But I guess, yeah, he was the first person who started talking about this new primitive called rollups. And rollups were this magical solution which gave you the guarantee of Ethereum, like the same security as Ethereum, and at the same time, at 10x, 100x cheaper rate than using Ethereum itself. And the concept was pretty simple. So the concept was that what is the issue with all of these transactions being sent to Ethereum? Ethereum had to compute it, right? So what it meant was that every time I send a transaction, Ethereum takes the transaction, it runs it in its virtual machine, and this computation means that gas has to be used. And if gas has to be consumed, that means it's it's going to fill up faster. So what John Edler described in his paper was that if you take just Ethereum and then you allow people to just post transactions, so they're just publishing transactions, they're not publishing anything else, right? And then rather than executing those transactions on the layer one, now you execute them in this other particular place, which you call as a rollup, or you can even call it a layer two, right? So you take some state, and the state is kept on Ethereum. And this is the role of computation, right? Computation in most of the scenarios, until unless it's stateless, takes some state and gets you to some other state. So you take some application as zero, you take the transaction you want to do on this application. But rather than doing that transaction on the application on the Ethereum L1 itself, you do it in this other place, this other computer, which you call a rollup, and you do the computation here. So the computation for transaction zero, let's say if this transaction was zero, so computation for transaction zero happens here. And then you take the new state of the application and then you post it back to Ethereum. So if you look at it, rollup is kind of like this computer where you are delegating your compute to. So it's like Ethereum is saying, hey, listen, I can only do finite compute in a block. So rather than computing transactions, I will just record them. So there's a proof that this transaction happened on Ethereum. And once this has been achieved, I will just send it for execution to this some other entity. And then people started coming up with various solutions. So now the natural question is, how do you prove that this computer is doing its computation correctly? This compute unit, which we are calling a rollup, is doing whatever it is doing in a real correct manner. And that's where people started working on various techniques, right? One technique was, which we call as an optimistic rollup, where the idea is that you're optimistically believing that all of the states that a rollup is giving, right, are correct until someone decides to challenge them. And then you will play an on-chain game. And part of this on-chain game is actually running this transaction again on Ethereum to see if whatever this rollup did was correct or wrong. If what the rollup did was wrong, then you can just slash the rollup. And the slashing being in place is an incentive for someone to never publish wrong blocks. And this has its own pros and cons. Optimistic rollups initially were very, very cheaper compared to zkRollups, and I guess they still are. And at the same time, the con is that because it's an optimistic game, you have to wait at least from 7 to 10 days, depending upon rollup to rollup and your game design, for a transaction done by a rollup to be considered final. So the finality is 7 to 10 days, which could be concerning in certain scenarios, and there are ways to move around with it. Now, that's where but on the other side of it are zkRollups, and that's kind of the thing that we will talk today. And zkRollups are pretty interesting because if you look at it, like what does the Ethereum does, right? Like Ethereum has this virtual machine, and that virtual machine is called the EVM, right? And this virtual machine can do any computation that you give it to. And then there is this other piece of software which is called as a node, and then the node exposes an RPC, right? And then the user sends a transaction via the RPC, and then the node executes the transaction via the EVM, right? And let's say there is some database that is attached here with the EVM that the EVM uses to repeat record of data, right? Now you can actually prove, like you can actually zk prove the EVM, right? And I guess everyone, because everyone was detected like my last talk, I guess you have already learned a decent amount about zero knowledge proofs. You can actually create proof of integrity of the computation that is happening inside the Ethereum virtual machine, which means if you can prove the EVM, right, then it means that you can prove anything that's happening on Ethereum. And uh, that's where like companies, I would say Polygon and Starkware took a slightly different approach, but I would say that's where like Polygon created the zk EVM. And the way the Polygon zk EVM worked, like the Hermes run, was that here is Ethereum, and then you as a user, your transactions land here in a block, right? So your transaction one lands here, and then the state of the rollup is here. And then you could say, here is Polygon zk EVM, right? And then there is this block, a Polygon zk EVM block, which includes these transactions. So it will take your transaction one, it will apply it to an EVM. It will apply this transaction to this new thing called as a zk EVM. And then this EVM is a provable EVM, right? So you have written it in zk circuits. You have like taken various, you written it into arithmetic circuits, and then you are proving its computation, right? And then what it allows you to do is that you take this transaction, and this EVM will return the next state for the application or the rollup along with a proof that it's correct. And then what you can do is you can take this, and in the next block, uh, settle the new state of the rollup. So you can say that if transaction one was applied on some state as 0, then this would be the result. S1 would be the result. And here is a proof that you can verify in just in the next block itself that this is indeed correct. And that is like a ZK based rollup. That's a ZK rollup, right? So you are like taking transactions, you are doing them somewhere else, but the virtual machine that you're doing it in and the other like peripheral software around it, you've written it into ZK circuits. And since you have written it into ZK circuits, you can attach a ZK proof that this is indeed correct. By the way, one thing to understand is that when we say ZK proof, actually no ZK EVM is actually ZK. Like they are just provable EVM. So I would say, like for example, Starknet doesn't use ZK stocks; it uses stocks. And what I mean by that is that in case of a ZK rollup, there is no privacy. Like it's like everything is still public. It's just easier to verify. Like you can verify all of it like in a single particular instruction. And that's why I think the word zk rollups is slightly uh, weird sometimes, because none of them are actually zk rollups. And the right word, according to me, should be validity rollups. So that's like a good right word to use for them. But this is like a zk rollup construct. This is a very simple one. Like in a real world setting, like you will have these entities called sequencers, and I can talk about them later on if someone wants to understand more about them. And there are like various kinds of guarantees that a rollup has to give. But this is a very, very basic description of how a zk rollup would work. Now, the interesting thing which has happened in the industry, and I guess something which might give you an edge in terms of knowledge around zk rollups, would be a zk VMs versus circuits. Now, to give you an understanding about this specific topic, like, so if you remember, like, thing that makes a ZK EVM or a ZK EVM based rollup possible, or any VM based rollup to be ZK proof possible, is for someone being able to write arithmetic circuits for the EVM. And believe me, it's a very hard job. Like, it's very hard to find people who can audit these circuits. Very few people can actually write them. So the talent who can do it is very expensive. The auditors who can audit it is very expensive. The security is very hard, hence, because it's like very few people can actually understand whether they are correct or not. And that was the initial challenge, right? Like, building a zk AVM was an AGI level of problem in crypto back in when Polygon only started it, and that's why, like, all of these organizations like zk Sync, uh, Polygon, like, they had spent huge resources, like more than $100 million into building one. And the way Scroll and Polygon, all of these other things were building it, was that they were taking the EVM and then they were writing circuits from scratch. So they would write a circuit for fetching memory, so circuit fetch memory, right? Then, like, a circuit for the machine stack, and let's say another circuit they will write for some op or the opcodes, so the circuit for some opcodes, and like there would be like so many of these circuits, and then they would combine all of those circuits together to like make a zk EVM, right? And then of course, like, you could say circuits for precompiles, and like a chip, or you could say like precompiles, and then you combine all of this together, and then you get a zk EVM. And that's how the industry worked in its initial phases of these, that you write like a virtual machine and its peripheral software from scratch in these really complex hard circuits. And the issue is that it takes a lot of time to be able to do so, and it's extremely complex, it's extremely hard. If you want to know how hard it is, imagine writing an EVM in assembly. That's how hard it can get. If you're building all of these things in, uh, let's say, like the very early forms of technology that are running. And the issue with this is that, first of all, it's very expensive to build because talent around this is very expensive. Second is, again, the auditor problem. How do you find auditors that can audit it? And they are expensive as well. Third thing, which I would say is even beyond the problem of cost, is that it's very hard to make changes to it. What I mean by that is that if you want to extend the EVM or any other virtual machine, and you want to add new features, it takes a lot of time to do so, because like, you again have to like write like a new chip from scratch, and that really affects the development time and the rate at which you can do new great features on these VMs, right? And that indeed became a problem, because now all of these rollups that came up on Ethereum were just exact clone of Ethereum, apart from the fact that they are just zk provable, and most of them actually had few precompiles missing, which means that like they couldn't even do some stuff that was possible on Ethereum, which meant that to some degree, as an execution environment, they were a downgrade. And that's where like the magics of zk VM started to happen. So what uh, like a zk VM is that it is a virtual machine that is designed from scratch for performance. So it's designed from scratch for performance in a zk setting. And what does it mean? Is that there are certain uh, curves which are hashing friendly, which are zk friendly, right? And if your virtual machine operates on those curves, and if the hashing algorithm it uses is optimized for zk, it means that your virtual machine will perform very better than taking something like the EVM, which was never meant to be zk proof, and then try to zk proof it. So a few examples of the zk VM side would be Cairo. So the Cairo VM was one of the first, and I would say one of the best implementations out there. Then there is Risk Zero. Risk Zero came up. And what risk zero allows you to do is to take any risk five code and then zk prove it. And then you could say there is SP1, so like which is like another new one in the market. And yeah, like SP1 is similar to risk zero. It allows you to prove any risk based code. I guess there is Fluent, and Fluent allows you with a WebAssembly. So you could say like all of these implementations scaled up. Now what they allow you to do is that a zk VM has a very high level programming language in which you can write, and these languages look very Rust-like. So, for example, in case of Cairo VM, it is Cairo, which actually sometimes get confusing because the name of the VM is Cairo and the language is called Cairo. And then in case of Rust Zero, you can take any Rust or any other language which compiles to this file architecture. Same in case of SP1, same to some degree in case of Fluent, anything which can be compiled to Awesome. So it allows you to, they allow you to write programs in a very high level and then be able to prove them. So what people started thinking was that, okay, what if I take an EVM which is written in Rust, and if I put it inside SP1, then I get a zk EVM. So it's basically taking the SP1 or the risk zero VM, running an EVM inside it. And if you're emulating the EVM inside the zkVM, then it means that you have a zk EVM. And the advantage is that you don't actually have to write any circuits from scratch. You can just take the Rust code, which already exists for Rest, and you can take REVM and any one of that stuff, and you can just create a new zkVM from scratch. And then there's no need to go through this complex design of designing chips and gadgets and then combining them to create a zkVM, which means that you can create all of this in less than a month in certain scenarios. So I was involved, I was fortunate to be involved with one of these companies. It was called Kakarot. And Kakarot takes the Cairo VM. So it takes the Cairo VM and it runs the EVM inside it. And then it allows you to, it eventually gives you a zk EVM. So now that's where the industry, I believe, is moving, by the way. I think everyone is slowly looking into it. I guess Tyco is going this way as well, where let's say there are these highly performant zk VMs, and then any other VM like the EVM, which has legacy, uh, which has, let's say, some legacy and wasn't designed with zk in mind, will eventually be emulated inside all of these zk VMs and will become zkRollups. For example, we are doing the same with Fuel, where we are taking the Fuel VM and then trying to probe it through SP1 and RISC-0. So that's like the new thing that has happened in the industry, like this new move towards zkVM architecture, zk EVM architecture. So yeah, that's like about zk based rollups. I see that there is like some 25 minutes left in this call, but I would say like I have tried giving some idea around what a zk rollup is on from my side. And I guess I'm more than happy to entertain questions now because I can keep going on around various other things, X, Y, Z, the state of the industry, and all of that. But I'm more than happy to answer any questions. Uh, Tell this problem. By the way, like, did what I say, like, made thanks, Seth. Yeah, but like for everyone else, like, did it make sense? Like what I said, like, I'm more than happy to explain anything which didn't make sense on like anyone said. Uh, okay, cool. Yeah. So I guess like we have like two options here. Like one is you can ask any questions around this. You can ask any questions around rollups. I'm more than happy to explain any of those questions. Or if you want, then I can attempt to talk a little bit about how Tornado Cache was implemented. But that is, I would say, might be a good uh, to deep dive into sequencer, centralized part. Ah, okay, got it. So cool. Uh, okay, I guess like, do we want to understand sequence? More than okay. Let's just okay, cool. So here Heather was asking, can you elaborate again in EVM running inside the Cairo VM? How exactly does it work? Okay, cool. I guess we can take this question and then try to explain the components like sequences. Uh, cool. So here's the way to understand it, right? So let's say this is Cairo VM, and the Cairo VM, what it eventually allows you to do is that it takes in a program, right? Like it takes in a program, and any program that you take in it, it can generate a result of running that program along with a proof that it is correct and which you can be verified efficiently um, as part of or like as part of the result, right? So you get these two things. So you can think of a Cairo VM as this black or like as a magic box where you put in any computation, any program, it executes the program, and it comes out with these two components. Like there's a result, there's a proof. Now, uh, what if? So it means that if my program is 2 plus 2, then it will just do 2 plus 2, and it will result, let's say, it will give me the result 4. Along with it, it will create some zk proof. It will create some object like weird looking object, and this object will be my proof. So first of all, like, does that make sense to you, Heather? I hope I'm pronouncing your name right. That okay, cool. So now, if it eventually can prove any program inside it, right? So what if you take a high-level language like Cairo, which looks a lot like Rust, and then you write the Ethereum virtual machine in Cairo. So you write EVM in Cairo, because at the end of the day, the EVM is just a pure, simple program, right? It's just if you go and take a look at the EVM, it's just normal REST code. That's it. Like it's deterministic REST code. It doesn't talk with the internet. It doesn't even connect with the internet. So it's just pure, let's say, just pure deterministic code. So if you take this EVM in Cairo and then you compile it as a program, like as a Cairo program, right? That's a Cairo program. Then what you can do is you can take the Cairo VM, put the EVM here, which is like EVM in Cairo, like this program. You can take the inputs from which is actually transactions, right? So the input of these programs are transactions, and then it will produce an output, and this output is like the new state. So you can take as inputs transaction, uh, previous state, and then it will produce like an output, and then the output will have like new state. So state S1, and then it will also produce a proof, just like how it does for every normal computation. So you just took the EVM, you wrote it into a high-level language, a compiler compiled it into a program that the Cairo VM understands, and then the Cairo VM takes your inputs, which is let's say transaction and like previous state of the rollup, and it runs the EVM program inside it with these inputs. As a result of this computation, you get a new state, and then you also get a zk proof out of it. And that's how, and since it's an EVM inside Cairo, it means that you are actually zk proving the computation of the EVM. So does that make sense? Like, no. Cool. So cool, that's good. I guess now Saf asked about the concept of sequences. Um, cool. So what are sequences? By the way, like in various blockchains, like so this is like my definition of a sequencer, but I've seen blockchains combining sequences and block executors and other entities like that. So in various blockchains, you might see something which is called as a sequencer also doing something what a block builder would do. So sometimes in a lot of rollups, these terminologies are mixed up a little bit here and there. But I will give you like what I think should be a good canonical definition of a sequencer. So, uh, as we discussed in the EVM, like a roll-up model, you have a layer one, and for example, let's call it an Ethereum. We call it Ethereum. And what the layer one does is that you send your transactions to the layer one, and then the execution happens on a roll-up. But the issue is that if every user individually sends their transactions on the layer one, then it will be extremely expensive because the layer one is expensive, right? And on the other hand, let's say the layer two, and it's also like it will also take time because if I send a transaction first on Ethereum, then I have to wait for ETH to get to finality before my rollup can actually go out and execute it, which is an issue because it's such a poor UX, right? Like L2s would be really slow if we operated this way. So now, what rollups do is that they have this entity called a sequencer. And what a user does, or what users do, is that they send all of their transactions to this entity called sequencer. And what the sequencer is doing is that it is saying, hey, like you have sent me a transaction, I am giving you a guarantee that I will send it to the layer one. There is this other entity called the block builder, and the block builder is taking transactions from the sequencer, and it is building layer two blocks, right? So it is executing them on the layer two, and like it's kind of like a promise scenario where the sequencer is saying, hey, I've included your transaction, builder yesterday, I've built your block. All of these users who are on the layer two can just work on this promise and continue doing their business, continue applying their business logic. And then it is eventually believed that this sequencer will take all of these transactions and batch all of them together in a single transaction and send it to Ethereum. And this allows the sequencer to use a lot of compression techniques, and this makes transactions cheaper for the users. And at the same time, they get execution very fast because the block builder is directly taking these transactions from the sequencer and executing them. So it's way faster than waiting for a block to be confirmed on Ethereum. Now, the question might be, why then even allow someone to be able to send a transaction from the layer one itself? And this concept is called forced inclusion. And the reason why you want to still allow for someone to do something like this, as we discussed here, where they can send a transaction on the layer one and the rollup is required to execute it, is because this entity, the sequencer, can actually try to censor a user. The user might want to withdraw their funds, but the sequencer might never accept this transaction, not enabling the user to take back their funds. And in that scenario, if you just allow a user to make a deposit from the layer one itself, it forces the rollup to process it, which means that you are guaranteed censorship resistance, even in the case a sequencer is there. Now, this sequencer, as Saf said, right now are centralized, but you could say they are like the real deal, the real business in the rollup ecosystem or the rollup concept. Because imagine if you are the middleman through which all transactions on the rollup are going, and you have the right to order them any way you want. Imagine the amount of MEV you can create. MEV. So, like one example of MEV could be that, let's say, some sort of various sort of just front-running attack. So, let's say if you send me a transaction and I look at it and I say, oh, I can if I just send my transaction before your transaction, I will make X, Y, or Z money out of it, because the order at which these transactions are applied will determine the new state, which means that whoever decides the order has real power. And right now, what rollup teams have done is that they have this centralized sequencer, and so it means that they are running the sequencer, and they are trying to be credibly neutral, which means that they do not apply any MEV, or they have some very finite formula to calculate how the transactions will be prioritized. And that's why everyone is trusting these teams like Optimism and all the other teams out there, Arbitrum, that they won't, let's say, ever do any MEV on their transactions, and the world is working in this way. But ideally, what you have to do is that you have to actually decentralize this role. So it means that if you have Ethereum and if you have the rollup here, so you actually want multiple parties to be running a sequencer. So like you want a decentralized sequencer set where like these sequencers elect a leader ideally every one slot, and then all the users send their transactions to the specific leader, right? And you want to do it firstly for the liveliness part, because imagine if the centralized sequencer goes down as it has gone down previously a lot. It means that like the rollup has stopped working, and then a normal person like me and you have to read solidity code to understand how do I send my transaction from the layer one, and it's absurd, right? Like that someone has to go through it. The second part is also that it levels up the playing ground, where it is saying, okay, now the sequences have been decentralized, and they have staked some amount, and they get the right to sequence a specific block, and they get the right to do MEV in it if they want. And this allows for the sequence of fees that the rollup is being generating right now. I guess I guess like Base was generating some crazy fees. Like Base was generating some $2 to $4 million uh, a month, kind of a fee, something like that. And right now, all of that fees goes to Base. That's it. Like that Base is the sole entity which takes all the fees from the sequencer for now, or for the say for the block builder for now. And decentralizing the sequencer and block builder will eventually allow for all of these fees to be distributed as well, and making it a truly decentralized system. One thing to understand is that there's no need for a decentralized sequencer to be as decentralized as Ethereum itself, because they actually cannot do anything extremely wrong. They can just provide do censorship, but you can always do forced inclusion from the N1. So that's why you do not have to, let's say, bootstrap the economic security of Ethereum for every rollup. And then there are companies like Espresso and Astria, which are building a shade sequencer, where like the same sequencer can be used to sequence transactions for multiple rollups. So yeah, that's about sequencers and what they do, how they operate with block builders, how they give you faster finality on the layer. Yeah. What is the relationship between the sequencer and the mempool? Does the user get into the mempool at all, or does it get directly submitted to the sequencer? Okay, good question. So, like, first of all, like, mempool is a very it's a very implementation specific thing, right? So, for example, if you look at Solana, it has no mempool. Like, Solana nodes just streaming transactions, and they're just accepting and executing it, right? Now, in case of a sequencer, like from my canonical definition of a sequencer is a lazy ledger, right? So it's a lazy ledger. It's this very dumb machine uh, which just allows you to post data to it. That's it. So, for example, how Celestia is for data availability, and it's a lazy ledger. Sequences are also, you could say, a lazy ledger, or uh, like it's like a not even lazy ledger. I guess this word should be dirty ledger, something like that. Like it's like nothing is happening. It's just a ledger, and no execution actually happens. So, in case of the sequencer, uh, it can depend from, let's say, implementation to implementation. So, in some cases, the user might send their transactions uh, to, okay, yeah, actually, this is how it will happen in most of the settings. Barely anyone will directly send your transaction to the sequencer. So yeah, ideally what will happen is that you will send your transaction to this entity called the block builder. So here is, let's say, your layer 2. Here you are as a user. And I can talk in the context of Fuel. You can send, let's say, your transaction to this entity called the block builder. The block builder will have its mempool, right? And it's like it has won a slot to build a block, right? And then the block builder will send the transactions eventually to this entity called the sequencer, and then the sequencer would eventually send it back to the layer one, or in case of something like espresso or anything else, it might just have a bridge with, let's say, um, it might just have a bridge with layer one. But that's like how it will look like in most of the cases, I believe. At least if I have to design it, this is how it will look like. Like you will send transactions to a block builder, which takes transactions, builds blocks, executes them, and then it's send this to a sequencer. And then once the sequencer has accepted it, then you could say there is like sort finality on the layer two, and then the sequencer will send it to the layer one. On the other hand, I also think that actually the second way is also possible. It all depends upon how you want to implement it, where the user can directly send the transaction to the sequencer, and then the block builder can build the transactions based upon whatever is being sent on the sequencer. This is also possible. I would say the difference between this approach. So is the L1 being bypassed when transaction is originally submitted? What does it mean to be bypassed? I didn't get it. Can you elaborate what do you mean by bypassed?
Oh, okay.
Yeah,
I didn't
yeah,
realize I
please
could
do.
talk. Okay. I guess my
Oh, yeah.
question is, so when the transaction is submitted, let's say Ethereum, when the transaction is first submitted, like normally it would go into the mempool, but you're saying it's first submitted directly to a block builder on the L2, or does it go into Ethereum first and then get sent to the
Oh,
L2 block builder? That's what I'm confused about.
yeah. So, like, both settings are possible. Ideally, so you would take the route where you would actually send it to Ethereum first, only when you think that the block builder, this entity, is censoring you, right? But otherwise, you will directly send it to the block builder or the sequencer. It can depend upon the implementation to implementation. And then it's kind of like a pinky promise between you and the block builder that they will eventually send your transaction to Ethereum. So that's a kind of how it will work. That in 99.99% of the cases, you will send your transaction to the block builder. The block builder will give you like a small pinky promise that I will send your transaction, I will submit your transaction to the layer one, and then you will just do any business logic that you want on top of this soft finality or guarantee. But if you think that, oh, like this builder isn't including my transaction, and that is really wrong, like I'm being censored, then you can send your transaction directly to the layer one, and then the builder will be forced in the next batch to actually include your transaction. So it means both options are available. You can send this transaction directly to the layer one mempool and it will be accepted there, and then the rollup has to do it. But that's a very slower route of doing it because you have to wait for ETH to get finality before you can get guarantee, the builder will execute it. On the other hand, the second approach is that you give it to the builder. The builder gives you a promise that I will send your transaction to the layer one, which means that eventually all transactions do reach the layer one in a complete ETH, like in a complete ETH secure rollup. And you just work on this promise. Does that make sense? Like,
Yeah, thanks. So I guess when we say the user, I mean, obviously the user itself isn't actually making these decisions, but we're talking about like whatever dApp it is that's connecting to whatever chain it's connecting to. Yeah.
yeah. So like, like the user would never even know that what's happening behind the
Yeah.
scene.
So the developer has to decide whether or not to send the transaction, where to send the transaction, I guess is what I'm saying.
Yeah. Like, and it will also depend upon like how the rollup has designed it. For example, if the rollup requires something to be sent to the sequencer first, then might differ. But eventually, like the all rollups will define on specific configuration of what does the transaction flow look like, which entity it first goes to, and then the dApp developer will just follow it behind the scenes. So it's just like Ethereum, where if I'm on a Uniswap, then my transaction goes to this RPC, and then the DApp is abstracting away all of that logic. It is sending it to a node, and then the node is broadcasting it to, let's say, other peers, and then that's eventually getting included in Ethereum. Similarly here, like the apps will be abstracting all of that logic away, and the user would never know. Like,
okay, I guess I'm just thinking, like, if you're developing something, is it clear, like, if you're developing for a certain, like, zkRollup as a developer, like, what you're supposed to do? Like, how do you know? Is it documented? Is it documented to say, oh, this is how you do it? Or, yeah, how do you know? Do I send it to the blog builder first? Because normally, you know, you don't have to think about it. You use Ethers or Veeam or something, and it just goes to Ethereum.
yeah, so right now, you do not have to actually think about it as an app developer in most cases, because they will just provide you an Ethereum like RPC, and everything happens behind the scene. So like
Okay.
a builder, yeah. So a builder is just, so in case of an EVM rollup, like an EVM based rollup, the builder will just be a get node. That's it, and you are just being exposed like an RPC link, and you're just sending your transaction to the RPC, and then this node is responsible for getting your transaction to the builder, or if the node is the builder itself, great. And then the builder is further responsible for sending it to the sequencer XYZ. But you as an app developer, until unless you're developing something very deep, would never have to care about it.
Okay, thanks. That's what I wanted to know, because I'm started thinking, how do I know what to do? But okay, that's clear.
Oh yeah. Like so a lot of this stuff, like most people would never even see that it's happening behind the scene. It's like, it's just deep architecture.
Okay, thanks.
Cool. I guess we have like 2 minutes left. So more than happy to answer anything else on my end as well. I guess it was good, at least on my end, that I got to revisit few stuff myself and and think through for myself as well. So yeah.
I think it kind of gives us some cues about, you know, how good a whiteboarding session like this could be, rather than, you know, going over some slides, fancy slides that are, you know, hard to understand. So that's,
Yeah, the whiteboard was good.
Yeah. By the way, like it all happened out of like it wasn't actually planned. I texted staff that I actually don't have any presentation for it. So the max I can do probably is some whiteboarding and sketching. But even I enjoyed it more than like
amazing.
just those presentations there.
Yep, amazing. Thank you again. Well, let's have one last question, if there is any. Go ahead, Heather, if you were asking something.
No, I've asked my questions. Thanks.
Okay. Is there anyone who has a question? If not, then again, thank you everybody for joining. This really was amazing, even for people who are in this space, you know, to go through this and kind of get a reminder. So Harsh, thank you again for your time. Really appreciate.
Yep. And I am on Telegram, so I cannot guarantee fast answers, but if you ever feel that there is some place where I can be helpful, or just speak more than, feel free to bounce the question. I do try to answer as many as I can.
You can join Harsh's lazy ledger, and he will sequence it based on when he can.
Yeah, I will. You can send it to my mempool and I will process them. I am a very slow chain, so it takes decent amount of time sometimes. But yeah, more than happy to help. Thanks everyone, and yep, thanks for inviting, and see you all.
Thank you.